Hey guys, so this is for anybody that just wants to study a little bit, or if you need to make up the natural selection artificial selection lab that we did. So today we're going to be looking at natural selection. There are 3 different types of natural selection, and they're all influenced by something called selective pressure. Okay, so let's take a look at what selective pressure could be. But first, before we do that, let's look at a graph. This is the kind of graph that I'll be using throughout this lesson. So if you're doing the activity, it says to draw a selection graph demonstrating that pattern of natural selection. And this is what I mean by a selection graph. So you've got kind of your y-axis and you've got your x-axis, and on your x-axis you've always got a gradient of phenotypes, whether that's color or bacterial antibiotic resistance, or if that's the amount of food you can get, or any of these things. That's always on the x gradient, and then y-axis is always going to have the number of organisms. So the higher up, the more organisms you have. Okay, so what this graph would be saying is that in this population of mice, there are only a few light-colored, only a few dark-colored, and then most of the population is living right in here, in the middle gradient. So that's kind of how you read these graphs, and then with these graphs, something is always influencing how these populations are surviving and reproducing. And so that thing that's influencing that is called selective pressure. And I'm going to use a green or a blue arrow to show selective pressure. Selective pressure is the thing in an environment that's causing an organism not to be able to survive and reproduce. So what I mean by that is that for example, we'll stick with our mice. If selective pressure in this case is applied against the darker and the lighter mice. Okay, so these guys and these guys are not surviving. They have selective pressure against them. And so what that selective pressure might be, it could be a cat, or it could be just a lack of food or something like that. But selective pressure is whatever is causing the organisms in an environment to not survive or not be able to reproduce. So in this case, maybe you have a gray environment, and so the gray mice blend in better, and the cats or whatever's hunting these mice are not able to kill them as well. Okay, so the selective pressure is acting against either extreme, in this case as represented by the blue arrows. So there's a few different types of natural selection. So there is directional selection, and that happens when the selective pressure, as we can see by these blue arrows here, that's when the selective pressure is against one side of the graph. So it's either pointing against this side of the graph or this side of the graph. Okay? And the selective pressure means, in real life terms, not in graph terms, means that in a population, so let's stick with mice, in a population, that side, so with mice it would be that color is not able to survive and reproduce as well. Okay, so in this example, the white mice are not able to survive and reproduce as well as the black mice. Okay? So if this happens long enough, then we expect the white mice population to go down, right? We expect this number to go down, number of organisms over here, to go down, and we expect the black mice population, the number of organisms in the black, to go up. And so what that would kind of look like, I'll try to draw a graph for you real quick here, is it went from this to something more like this. The dots represent the new graph. So do you see how the graph just kind of shifted over to the right? I know that's kind of hard to read, but that's the idea of directional selection. The graph is moving in one direction. It doesn't have to be to the right. It could also be to the left, like this. Directional selection is when you have selective pressure against one side of the graph, and it pushes the population to the other side of the graph. So the population increases on one side, this side in this case, and it decreases in the other, and it makes it look like this. It shifts everything over. The graph still has the same shape, it's just over to the right or over to the left a little bit more. So that's directional selection. So an example for stabilizing selection is when we see the selective pressure acting on both extremes. So if the selective pressure is acting on this extreme and this extreme, we see stabilizing selection. And a good example of stabilizing selection is baby weight. So babies that are born that are super heavy. So these babies over here, like 14 pounds, 12 pounds, they are really hard to give birth to for the moms. And so really heavy babies tend to not, in the past, a long time ago, before we had really good medicine, heavy babies tended to lead to more miscarriages and death from the mother and for the child. And so having a lot of weight when you were born was not really a good thing. And so that was selected against because bigger babies tended to not survive as much. And then the lower weight babies, right? Have you ever seen those really small babies that can fit in the palm of your hand, like the 2-pound babies? They also can't really survive outside of modern medicine, okay? So the best weight for babies, the most likely for babies to survive is if they land in this range, anywhere in the 8 to 10. The extremes, 14, and the extremes 2 are both selected against. So you can see that by the blue arrows, and I'll just draw for you an example of what stabilizing selection would look like over here. So you got your graph. Just pretend it's the same x and y axis, and instead of looking like this, it's going to be even more emphasized now. So stabilizing selection after 20 generations or something like that, 20 generations of babies being born, is going to look like this, even more strongly high and even lower on the extremes. You see that? So it's even lower on the extremes and even higher in the normal. So that's stabilizing selection. So that means it's stabilizing selection. It's selecting what's already normal, which is this 8 to 10 pound baby weight. It's selecting for what's already good in that population. So our last example of natural selection, the last type of natural selection, is called disruptive selection. And this is actually the most rare type of selection. We don't really see this in nature a whole lot. And so I had trouble coming up with some examples. One example that I found was an example from these two scientists named Thode and Gibson. And these guys were scientists, and they would literally just have a bunch of flies in a jar, and they would count the number of bristles on the fly's legs. So they would count the number of bristles, and if the flies had a lot of bristles, like 15, they would let them reproduce, and if they had 3, they would let them reproduce. But anything in the middle, so anything in this range and over, they would not let those flies reproduce. So the selective pressure is Thode and Gibson in this case, and they're not allowing anything that's usually normal, so anything from like 4 to 11 reproduce. It has to be lower than 4, fewer than 4 bristles, and higher than 11 bristles to reproduce. So disruptive selection selects against the norm, it selects against what's right here that you typically see, and it favors the extremes. It favors your like 15s and your 3s. So with our baby weight, an example of that would be it favors the heavy babies and the really light babies, okay? That doesn't happen in real life, but this did, this bristles. So what we saw, an example of how that looks, is you make another graph, pretend the x and the y-axis are the same again. So we've got our selective pressure coming right here down the middle, and how that's going to change the graph is the middle, what's most common, now it's not going to survive and reproduce as much. So the number of organisms in this population with 7, 10, 5 bristles, that's going to decrease. So that is going to look like this with our dotted line. It's going to decrease. And then the numbers of like 3 bristles and 15 bristles, that's going to really increase. So it's going to look kind of like this, right? And so our graph will end up looking like an M shape or a wave. So disruptive selection always kind of looks like a wave. You can see it looks totally different. It's literally the opposite of what the graph was before it, and that's why it's disruptive, because it's selecting against what was normally prevalent and instead favoring both extremes. So those are the 3 types of selection. We had directional, disruptive, and stabilizing selection, and it's all caused by selective pressure. So you should be able to answer the homework now. You should be able to get some examples and write down some graphs there. And also, I hope this helps you study for the test. Thanks. The last thing that we need to talk about is natural versus artificial selection. Natural versus artificial selection. And this is a pretty simple thing, shouldn't take too long. Natural selection is when nature is when nature is directing how organisms are changing through the generations. Whereas artificial selection is when men are the one that are changing. So man, women, it can be you too. I'm not trying to be. So it's when man is selecting the traits that we want in different organisms. So examples of those, natural selection would be like the beaks on the finches, Darwin's finches. These are all really different, right? No dude was capturing finches and breeding them for different beak size, right? We don't really care what finches' beaks looks like. And so nature just kind of shaped this naturally over many years and through through different environments. Some birds had big beaks and some birds had small beaks because big beaks were better for some environments and small beaks were better for other environments, okay? And then artificial selection is man-oriented. We are deciding what traits we want. And a great example of that is in wolves being domesticated into dogs. So we would capture wolves, right? We'd catch wolves, and then we would only let the really tame wolves breed. We would only let the wolves that were really tame have kids with other tame wolves, and if we do that over and over and over many generations, eventually we get these really cute, fluffy, kind dogs like this, okay? So artificial selection is governed by man, natural selection is governed by nature. Thanks.